Okay, guys, so welcome to the Robotics and Artificial Intelligence meetup number 63. And today the topic would be how you can learn reinforcement learning by playing popular games like Street Fighter, Tekken, Dead or Alive, and so on. So today we have a guest from Umbra.ai, which actually builds these reinforcement learning environments, and you can train several of the state of the art reinforcement learning algorithms on these environments to play these popular video games. So this would be super interesting. The agenda would be, after this really short introductory presentation from my side, I'll hand it over to Alessandro Palmas, who is from Diambra.ai, and who will be presenting the main topic for today. And after that we will have a short Q&A session, and so you can ask questions directly to him, and you can also actually try out the GitHub repository later as well, because this project is open source. And after that, if you want, you could stay for introductions and just casual networking. So these meetings are always recorded and shared online. So for those of you who join regularly, you already know that. And we have these podcasts and weekly meetups. And the idea is that we want to help you explore different areas and different projects in different subdomains of artificial intelligence and also in robotics. And at the same time, if you're doing your own projects, you can find accountability partners, and you can also ask for programming help when you get stuck while doing a project. So, okay, I think you guys already know of the framework that we have adopted to learn. So interestingly, this is also derived from the reinforcement learning standpoint of exploration and exploitation, and that means selection of your field, which comes under exploration, and then once you have explored enough of different subdomains, then you take up projects in individual domains, learn the necessary theory, find accountability partners, and showcase your project. And in essence, this is exploitation of one particular sub area in robotics or AI. So that is it, and you could refer to all of the resources, the GitHub repositories, the meetup presentations, and also the video recordings on YouTube or also on the website, thebuildingculture.com. So that is it. Without taking any more time, I'll hand it over to Alessandro. So over to you now.
Thank you very much, Shandandip, and hello everyone. I'm really happy to be here today, sharing with you this cool project that we have been working on for a while now in the RL domain. So let me start sharing my screen. Can you confirm you can see my screen?
Yeah, we can see your screen.
Great. So yeah, let me get started with my slides. Okay, so first of all, as Chandandip said, this will be the title of our today presentation, and then this is gonna be the summary. So now about me, 5 minutes, I promise. Very quickly, a few words about who I am and my experiences and the background. Then we are gonna deep dive into RL in practice. Very quick overview of main aspects of reinforcement learning. After that, a few words about the Umbra project. What is it all about? Main resources to take a look at. And at the end of the presentation of the Umbra, we are gonna see a trained deep RL agent live in Street Fighter 3 playing in these screens, and we are gonna see how it compares with the random agent. Then at the end, a few words about collaborations and the Q&A session at the end. Okay, so let's get started. About me, Alessandro Palmas. I'm located in Italy. I've been experimenting for a while in RL, but everything started for me from my background. I'm an aerospace engineer with a very big passion for programming. I had the opportunity to merge these two fields together in my daily job as a R&D manager in an aerospace and defense company here in Italy. And my passion for the entire general broad machine learning domain, especially in the subdomain of computer vision, gave me the chance to start project in that field inside my own company. And this is more or less what I do in my day job. At night, RL is the central focus of my efforts. Here I reported a few very important milestones, those of DeepMind and OpenAI, where they managed to train a reinforcement learning agent to beat professional human players in different games, either Go and Dota 2. At the end of this spiral, it's the Umbra project I started a few years back, slightly more than 1 year actually. Is a project focused, of course, on reinforcement learning, and I'm gonna share a few words about it in a few slides. So reinforcement learning. First of all, since I'm hearing a lot of connection and disconnection sounds, can you please, Chandanip, confirm you're still able to see my screen?
Yeah, your screen is visible.
Right, okay. So when you approach machine learning for the first time, a typical division of subdomains is the one that you can see right now on my screen. So they typically group different branches in unsupervised, supervised, and reinforcement learning. You can recognize here pretty common applications of machine learning, like image classification for supervised, predictions and forecasting for regression, again in supervised learning, dimensionality reduction or customer segmentation for unsupervised, and then there is reinforcement learning. So in a sense, they are usually grouped this way, even though, especially when you merge deep learning with reinforcement learning, a lot of techniques and approaches you find in supervised and unsupervised learning, you can definitely find them too in reinforcement learning. So it's a good first division from a very high level point of view, but they are all strictly connected one to the other. So when you approach reinforcement learning, this is what you typically find at the very first slide. So the reinforcement learning scheme, it's describing the interaction between entities that are involved in the reinforcement learning domain. And here, that standard scheme is represented through elements of the Umbra, so the Umbra project. And this is useful because you will see later that you will have a very let's say practical grasp of every single element of this scheme. So what is it all about? First of all, you have to notice that this is like a cycle. So it's like an iteration between an agent, that is the standard term that identifies the reinforcement learning algorithm on the left, and the environment, that is the standard term that identifies the problem in reinforcement learning, so the problem you want to solve. So the agent sends an action to the environment, and in the case of the Umbra that has to deal with video games, the action is, you can think about the action as a button pressed on your gamepad that is sent to the environment, that is kind of a wrapper of the video game. Then receiving that action and executing, the environment produces two things: the observation and the reward. The observation, you can think about it as the screen of your console monitor, for example, so your TV screen or your computer screen, that shows you the screen of the game, of the video game. So that's the observation. and the reward is a measure of your performance. So when you play in a video game, you take, you decide your action depending on what you see on screen, and this is what the agent is doing here. Now, the reward is a measure that tells you how good you are doing, and we are gonna look at fighting games. This is the main focus of the Umbra at this point in time. And fighting games, a typical measure of how good you are doing is given by your health bar. So if your health bar is full and the opponent's one is going down, you're doing good, and vice versa. If your health bar is going down and the opponent is still almost full, you are doing badly. Now, this is how reward is defined in this domain, but reward is is a measure of performance of the problem and can be defined in many different ways. So it's a very inner part of the problem itself. Depending on how you define reward, you can optimize something for something else. It will be even more clear later, but let's take a look at a typical code example for a typical reinforcement learning basic cycle. So, okay, first of all, and this is how you can do that with the Umbra Arena, and I will tell you more about it later. So, first of all, you initialize your environment. So you create your environment. And as you can see, a typical interface that is used is the so-called OpenAI Gym interface. It is the one that the Umbra Arena uses. So you create the environment and then you reset it. So in the case of a fighting game, this reset operation brings you to the very first frame of the very first round of your game. After that, the iteration loop starts, and as you can see, the agent select an action. Now here we are selecting a random action, and so in this case we are just deciding to press buttons in a random order. Then we send this action to the environment that executes it and returns observation, reward, and a done condition. And this goes on for a while. And as you can see, after the environments perform a step, it returns an observation, and the agent selects a new action. It sends it to the environment that returns an observation, and then again until the done condition is encountered. Now, the done condition in the example of fighting games can be either a game over, so you lost, for example, 2 rounds, and so you're done, or you completed the game, and in that case you are done too, and that's where the episode ends. It's important because to understand this, because these are what are called typically episodic tasks. So tasks where there is a clear start and a clear end, and this is how it works. So this is the basic cycle for reinforcement learning. Now, of course, here we are selecting random action. The goal of all this will be to create an agent that is able to perform optimal choices of actions. Now, in every single reinforcement learning problem, there is the observation space concept that describes what type of observation are available to decide actions. I mean, you or your agent, you need to take a look at something, the observation, to decide the next action. That the description of what kind of observation you will be looking at is the observation space. Of course, in the case of games, the typical observation space is composed by the screen pixel, but in our case, we also provide, together with the screen pixels, we also provide additional numerical values. So values that are all already available through the screen pixel. For example, health values, number of wins, characters that you are using and that you are facing, side of the screen you are playing, like left or right, these kind of things. Now, all this information can already be available and achieved by just taking a look at the screen pixels, but it can be easier for an algorithm to use them as a numerical value. So this is the observation space for the Umbra Arena, and is an example of a typical observation space in the field. Then there is the action space. It describes what type of actions you can select to interact with the environment. Now, in the Umbra Arena case, we have, of course, the interface is the gamepad, and you can create different action spaces depending on how complex you want to treat it. So the first choice is between discrete and multi-discrete action spaces. The only difference is if you want to consider moves and attack buttons in the very same way, so belonging to the very same set, or coming from two different sets. Now, if you consider move and attack actions in the same set, for every iteration, you will be sending either a move or an attack button. You cannot send them together. And this is, of course, a limit on one side if compared with the multi-discrete action space, because in that, you will be able to send at the same time move and attack actions. Now, the problem is that with a single set, of course, you are limited because you can send either a move action or an attack action, but you have a smaller number of actions, so like 12 or 16, depending if you want to use or not attack buttons combination, so pressing two buttons at the same time. If you use a multi-discrete action space, you will be able to send move and attack actions at the same time, but in this way, the action space becomes way larger, and so the problem becomes more complex. It's, of course, a typical trade-off between simplicity and completeness, like not having the constraint of a single set of move. But depending on the resources that you have, hardware, computational ones, you need to select the right trade-off appropriately. So what's the goal of reinforcement learning? Well, the goal is finding the so-called optimal policy. You are given this problem, in our case, let's say a fighting game, and you want to find the optimal policy. So something that links observations with actions, that for a given set of observations that, as you can see here, may be composed by frames and numerical values, gives you and tells you, okay, in order to achieve the optimal result for games, for example, it means in order to complete the game, you need to do, to select this action in this case, this other action in this other case, and so on. So this is the goal of reinforcement learning, finding the optimal policy. Now, to talk about solution methods for reinforcement learning, it would take a very long time. I will list down for you all a set of very interesting resources like books, courses, papers, and so on and so forth later. It's a long road. I can, try to going quick through it. This slide tells you that today, in order to tackle problems with a very large dimensionality like the ones that we are seeing here, they are not simple problems. The state of the art is represented by the fusion between deep learning and reinforcement learning that gives birth to the so-called deep reinforcement learning domain. It means that your policy is typically a deep neural net that links your inputs, so your observations, to the outputs, so your actions. In this slide that you are seeing here is represented the very first milestone in this domain, the DQN paper. That was the first success in using this technique applied to Atari video games. The approach is more or less the same every time. There are slight differences in terms of how different algorithms are derived, but the idea is more or less the same. Use the capabilities of deep neural nets to approximate very large, complex configurations of the environment to obtain results, to condense and select the proper actions depending on the situation in the game you are facing. So DQN was the first success. One of the latest ones is the proximal policy optimization. Is one of the most high performing deep reinforcement learning algorithms, and is the one that I used to train my agents in these games. And the one that we are gonna see in a few minutes has been trained with this algorithm. The policy network, the one that I told you about before, so the brain that is selecting the right action in the right moment, is composed by the elements you are seeing on screen. So there is a convolutional neural net that is extracting features from frames. Then there is a parallel fully connected neural network that is extracting additional information from numerical values. These features coming from these two networks are concatenated together and served as input to the fully connected neural net. And this is the one that decides actions. So this is the structure, high-level structure. We are gonna, go down into details about every single block of these networks so that you can have a detailed view of what's inside every single one. There are multiple interesting advanced techniques in the world of reinforcement learning and deep reinforcement learning in particular. I'm just listing some of them here so that you at least know there are. One of them is called imitation learning. So the idea behind imitation learning is, if I'm for example, a good player in a video game, I can try to record my choices in every single moment. So for every observation I see as a human expert, I can record the action that I selected as an expert. I can create like a collection of these, they are called trajectories. So I can create a collection of expert trajectories. And then I can use imitation learning technique to expose these trajectories to my neural net. In this way, for example, one typical application is called behavioral cloning. I can have my network emulating what I did as an expert, and so it would be cloning my behavior, and so trying to replicate my choices as a human. This is an option. This is one of the advanced technique. Another one is called self-play. So self-play is the idea of letting your agent compete against itself. In some sense, you make, in fighting games, for example, you can make your agent fight against itself and evolve together. At the very early stages, it will be just random, but then as they grow, they will be grow together. And so one of the good things of this is, okay, first of all, you are bypassing the problem of imitation learning that requires humans to play, and this is not scalable. While in self-play, since the agents will be fighting one against the other, you can do everything in parallel and without human supervision, at least with minimum human supervision, and this is definitely more scalable, and your agents will learn by facing opponents of the same skill level, more or less. Moving forward, another cool technique is called human in the loop. Now, human in the loop training comes into play when reward functions are not super easy to implement. It's not simple to define the best reward function that will bring your agent to the optimal behavior you want. So instead of just implementing the reward function in terms of mathematical formulas, you can integrate a human feedback in the loop. And just to give you an idea of this, let me show a very brief video about it. So in this video you're watching, the idea here is there is a human that is telling the algorithm which one on screen is the bad one. Better in terms of more, in the right path towards making the hopper, that is this robotic leg, jump, and do a backflip. Now, at the very early stages, it's clear that it's not super immediate to understand which one is better than the other. But as the training goes on, the human just needs to prescribe which one is better, left or right. There is no reward function implemented here, and so the human is just prescribing, you're just saying which one is better, and the training goes on this way. And at the end, you saw the algorithm was able to perform the right move at the end of the training, and this is just using human feedback. So no need to implement a reward function. That can be hard, tricky, and sometimes definitely not intuitive. But at the end, the goal is reached just using human feedback. Yeah, so that was about human in the loop training. Now let's talk about challenges of reinforcement learning. Of course, it's not easy in terms of theory. It's a complex topic, and so it requires dedication, definitely. And think about the fact that you are mixing, when you're approaching deep reinforcement learning, you are mixing problems, complexity of deep learning with complexity of reinforcement learning itself, that it adds up, let's say. And so it's not easy, but it's definitely a challenge, can be approached with the right attitude. Sample complexity, what is called sample complexity. You can see here in this screen on the left, there is a screenshot of Dota 2, a OpenAI 5, the bot trained by OpenAI to play Dota 2. One of the problems of reinforcement learning that is a current major limitation for it is the fact that it requires a lot of computational power to create good agents, because a lot of interactions between agent, algorithm, and environment is required. And so, as you can see on the right, there is a table showing you what was the infrastructure needed by OpenAI. So for OpenAI 5, you see here, they were using 128,000 CPUs and 256 GPUs. So they collected, for every day of training, they collected about 180 years per day of experience. So for them, it was like someone playing for 180 years every day. And this was the amount of experience required for their agent to reach a good level of experience, of performance. And this was their infrastructure. As I said, every single unit here is a single GPU that is interfaced with the 500 CPU for environment interaction and experience collection. And this is multiplied by 256 in the third dimension. So a very huge computational infrastructure. And this is definitely strictly linked with the sample complexity problem of reinforcement learning today. Now you can understand, since the very peculiar aspect of reinforcement learning is you don't need data sets. In reinforcement learning, you start with the random agent that is interacting randomly with your environment. So it's gaining experience of your environment in iterations. And as we just saw, there are a lot of interactions needed to learn. So this is the reason why you see reinforcement learning strictly related to virtual environments. And virtual environments are typically simulators and video games. So this is the reason, together with the fact that you cannot just, even if a huge amount of interaction was not needed, well, you cannot build a physical robot to interact randomly with the environment in the early stages. Like you cannot use a drone and try to make it learn maneuvers by just performing random actions in the real world, because in the very first episode it would crash. It's very likely, And so, of course, you first need to start from virtual environments and then trying to transfer the knowledge to the real world. Even though reinforcement learning is something that is very a cutting edge topic in research, its industry application has already started, and of course a typical application is in video games, because video games are those contexts where the simulated and the real environments are the very same. So there is no transfer learning problem. You can train something in a simulation, and the real application will be, if not identical, very, very close. But they are also being applied, or let's say first investigation started from the world of trading, the worlds of ads optimization, as well as usage in the robotic world, for example in the world of multirotor drones and similar machines. So it is something that is starting to move from only research topics to industry potential application. Now this is where I would like to share with you resources about RL that can be very useful if you want to approach the field. Let's start with environments, because if you want to learn reinforcement learning, you need to make sure you're also able to test what you learned in real problems. And so, as we just said, problems are environments in RL, and here I listed 3 different options in terms of environments. The first one on the left is OpenAI Gym. On the right you find Unity ML agents, 2 very famous resources. At the center, our own environment. It's called Arena, and it is the one on the left. Ray RL Lib is another very famous and very powerful reinforcement learning library. It also gives you the capability of exploiting parallel reinforcement learning. It's incredible. And finally, there is also, I also listed RL Coach. I never used it, but I know it's another option there. Now, in terms of books and courses, well, of course, this is not the full picture of what is available out there, but this is something that I've been using and that I can tell you works. On the left, there is the most important book about it, is Reinforcement Learning: An Introduction by Sutton and Bartow. This is the main reference. Everyone should start from that one. Then right beside it, you find the Reinforcement Learning Workshop, edited by Pac. I co-authored 3 chapters on that. It's a very hands-on. It also provides a GitHub repository to, together with the book. It's good for a hands-on experience. It can be a very useful resource. Then there are lectures. Deep RL Bootcamp by Berkeley. It's great. It's dedicated, in particular on to deep RL, and it's definitely a very, very important resource. It's super complete. There are people like Peter Abil there, John Schulman, the one that created Proximal policy optimization. So a great resource. And then there is a reinforcement learning lecture series by DeepMind and UCL. This is another cool one. I must say I haven't had the time to take a look at this, but this is wider with respect to this one, to the Berkeley one, because it's not only on deep RL, it's on reinforcement learning itself, more like the reinforcement learning book by Sutton and Bartow. After you complete your books and courses, of course, you have to go with papers. open access conferences and journals, because this field is growing every day, and so it's very needed, very important to keep an eye on papers. And finally, I strongly recommend taking a look at about it later, all the good things it provides. The second element is our REL community. We do have our own Discord server and our Twitch channel and other social channels. We want to group together people that are passionate about the REL, and so this is another good element of the Umbra. And finally, our AI tournament platform. We are building the platform where you will be able to submit your trained agents to compete one against the other in cool video games, so fighting against other agents, fighting to complete challenges, and so on and so forth. We are working on that. We are about to deploy the very first version of it. References, super easy. The Umbra.ai is the main website. On the top right, you can find access to many different resources from the GitHub repository, and inside that our documentation for it, then our Discord server, our Twitch channel, and our LinkedIn page, and so on. So about the Umbra Arena, we're about to start watching our agent. Why it is a good resource, and REL environments provided by it are a good point from where to start is, okay, first of all, we are providing cool, popular fighting games. And so it's definitely very fun to use these agents and to see them learn, because it's a very, you have to take a look at gameplays and understand where your agent is missing something, and so on and so forth. The dimensionality of these problems is tractable, so you can use these environments at home. This is very important, because I trained my agents using my own PC that is kind of, a low to medium level PC, and you can definitely use it. So it's good because you don't have to rely on very high powerful computing clusters. It's maintained and well documented. There is a very comprehensive documentation available. Support is directly available on our Discord server. For every problem you can reach us, and we will help you out. It's available for Windows, Linux, and Mac, so you can use on every platform. And there are advanced features available, like you can play against the computer, or you can play against humans, you can play against other agents, you can make your imitation learning experience. You can also have a human in the loop training, so it provides advanced features. Now, this is the policy we're gonna see playing in a very few minutes, and it's built in this way. So as I already went through it, and the detail is this one. So inside the convolutional network, there are 3 convolutional layers, and then they are flattened, and there is a final dense layer providing at the end 256 neurons, so features. On the other hand, at the bottom, there are 2 dense layers with 64 features at the output. Concatenated together, there are 320 features, latent variables, and these are provided as inputs at the final layer that provides, the action selected with the argmax with the highest probability. This is the infrastructure, the architecture of our network, and the training set, as I said, the single workstation with 8 CPUs for, actually this is the highest. I used 2 different configuration, one with 4 and the other one with 8 CPUs. single GPU, and I can tell you, even doing training only using the CPU is not a problem, because the bottleneck is not on the training the neural net, is on collecting experience for the game from the games. Okay, so let's move on, and let's take a look at the agents right away. So I would first go with the random agent, so that you can have a feeling of what a random agent is in these games. Now, I trained in Street Fighter. I trained my agent with in order to use a Ryu, one specific characters of those among those available, and so we are gonna watch first a random agent using Ryu, and let's just the graphic load, and then we will be able to start. So now let me warn you, it can seem that the random agent seems to be at least decent, because it could also it could even win some round, maybe, but don't get fooled by it. What you need to take a look is the score, not the rounds, and I can spend a few words about it later. So let's keep an eye on Ryu on the left now, so with the dark blue, or let's say gray kimono, dark gray kimono. Now he's on the right, and you see it is able to hit the opponent a few times, but it's performing like random actions, spamming buttons, and you can see those buttons pressed on the graphic. Now the point is, even if we are able to hit a few times the opponent, our score, as you can see right now, it's not so high. The score that is listed on the top right on the screen is the measure of how good we are. Okay, so so far we are minus 0.26, minus 0.23. Now we'll see. So even if we will be able, for example, to win this round, again, we lost the first one. So you see minus 0.34, something like that. Let me stop the random agent, because this is more or less the same. It's gonna be more or less the same the coming round. And let me instead run the trained one. Okay, so if everything goes as expected, we should be seeing something that is way more powerful. And let's keep an eye on the score again. So I would say the following. Since it's gonna take a while to see the entire episode, we can start having questions after the first round, maybe, and so we can let it play in the background, and at the same time start answering questions. So yeah, everything is loading up, and you will see at the very first step of the first round, the screen will freeze for a few seconds, and this is where we are loading our network weights. So network weights of our neural net will be loading up there. After that, it will play in real time, and so we will see how we'll be playing. So okay, now we are playing with Ryu. Okay, again on the left side. Let's see. So here comes the freeze for a few seconds, and then it will start selecting actions according to the policy. Okay, now take a look at the difference with respect to the previous bot. Okay, of course we won't be perfect. Maybe we will be able to perform some perfects, but it's not always perfect in every round. But still, you see, first round ended and our score is about like 1.8, something like that. And if compared with the previous one, it's clearly way better. And I can tell you, this bot here, this trained algorithm, is able to usually able to reach the final stage. And let's see if we will be able to complete the game. Now, there are 10 stages. This was the first one. I think we can start asking, taking questions. If you want, let me, if you want, Chonandip, we can definitely start now while keeping the the screen, the bot go in the background.
Yeah, I think we can start with the questions. So yeah, if anyone has any questions, you can ask now.
Perfect. You can, interrupt me when you want, Chandandeep. I will, maybe try to share a few information about this. So as I said, I used the stable baselines as a reinforcement learning library. I interfaced it with the Umbra Arena environment. Again, how to use the Umbra Arena is super easy. In our GitHub repository, there are references to the documentation where installation in a few steps is explained. And also, we provide in our GitHub repository, we provide examples. So you can use scripts that we have to getting familiar, to get familiar with how these environments are used. We provide at the moment 6 different games: Dead or Alive ++, Street Fighter 3, Tekken Tag Tournament, Ultimate Mortal Kombat 3, The King of Fighter 98, and Samurai Showdown 5 Special. So and we are already working on additional ones. And so this is how to easily get started with these environments. Definitely you can start from that.
Yeah, Alessandro, can you also share the GitHub repository on the screen and show everyone how how they can select environments? I know it's very well documented, but if you can just briefly share that. Meanwhile, if anyone has any questions, you feel free to ask.
Yeah, so let me go this way. So first of all,
yeah.
Can I ask a question?
Yeah. Please go ahead.
Okay. So thank you for sharing with us the Umbra repository. Looks pretty nice. Thank you, Alessandro.
Thank you.
My question goes in regards to the resource requirements for your environment. Do they only run in CPU, or do they actually also need GPU?
Okay, thank you for the question. So first of all, the environments don't need a GPU at all. Environments, okay? Let me also give you a comprehensive answer. So from our website, theumbra.ai, you can just on the top, you can click on the GitHub icon. You will be redirected to our GitHub repository. Okay, this is okay. Now this is the repository, and from it, okay, first of all, you have access to the entire repository. There are example folder here with all the environments, with all the scripts that you can run, and you can go in the documentation here very easily, and the documentation tells you everything you need in terms of how to set it up, how to install it, how to run, the first script that is pretty easy. For example, this is the shortest snippet that you can use to run the Umbra. It's a Python, of course, it's based on Python, and the interface is based on Python. So in order to import the module, you can just need import the Umbra Arena, and from there it's pretty straightforward. To select the game, you just need to change this keyword here. All the games available are documented here under environments, game and specifics. All the games you can find them here, and here you find also the game ID for every one of them. So the other life, for example, is Doa PP. Then in Street Fighter you see here, and so on. Now for the environment itself, you definitely don't need the GPU. You can just, it runs on CPU only, not a problem at all. And the GPU is usually good to have for training your neural nets. But as I already said, is not a mandatory requirement. I mean, training with CPU only is something that is definitely feasible and only causes a minor slowdown if compared with GPU training. The reason is, and this is true when you're training on your own machine, not on a cluster, because the problem is the following. The majority of time for these problems is required to collect experience for the game. So to interact with the game and save your observation, rewards, and so on. Then all those things grouped together need to be sent to the GPU that takes care of training your neural nets based on those experiences. And so the typical duty cycle of this for these games of the GPU is about 30%. So it's 30% of the time on, 70% of the time off. So it's definitely is not the bottleneck. You know, the GPU is not the bottleneck. So you can start experimenting with them and getting familiar with them even without the GPU on your machine.
Thank you. I have another question. You mentioned at the beginning of the presentation that you work in the aerospace
yes.
Field. I don't know if you can give us a small hint on how you're actually combining reinforcement learning and aerospace workflows.
Yes.
I don't know if you can.
Yeah, sure. Thank you for the question. Of course, I can imagine this is interesting. Also, every time for me, when I see a new tech, having a grasp of how this tech is applied in the industry is definitely interesting. So yeah, we are a space company, and as such, we are exploring reinforcement learning in at least 2 domains. In both of them can be, let's say, grouped in the or put in the robotics world, because we are exploring opportunities to use RL as a support for multirotor drones maneuvers, for example. And this, if compared with standard controllers, where reinforcement learning can have a good advantage is, for example, in building controllers, for example, for your flight, that are robust with respect to failures or maybe failures in terms of both actuators or sensors. Let's say that your sensor goes down because it faces a failure, or your actuator will go down because of the same thing. And your reinforcement learning controller could be more robust if trained appropriately, maybe in simulation, and being able maybe to face this kind of failure and still limiting damage during the mission. This is true for multirotor drones. But let's say for example that you want to train something that, in the meantime, we are arrived at the second last stage. Okay, this is the 9th stage. We will see how it goes. So let's say you want to program something to land on a planet that is outside the solar system, or in a comet that is flying around in the solar system, but you are not sure about, for example, the atmosphere density or the gravity force that will be affecting your rover right there. Now, with reinforcement learning and with the proper simulator help, you could train something to be super robust of these uncertainties. And so also, to make autonomous maneuvers, it can be a good solution to leverage reinforcement learning, because of the fact that you won't be embedding heuristics or specific crafted solutions. You will be let your controller face the problem itself in its different shapes and forms, and then it will just autonomously find the right solution for the problem. So this is where we are exploring these opportunities in the aerospace.
Very interesting. Thank you.
Yeah, thank you for the questions, of course.
Thank you.
We're reaching the final stage now. Okay, just a few things. Gill, the final boss for Street Fighter, is a very hard one, and in particular, it has a very specific move. It's called Resurrection. When the bar you see at the bottom is full and you beat him, he's able to recharge completely his own health bar, And that's, of course, a very complex thing to face, because it's like facing 2 rounds with a single round health from our point of view. So it's hard, and so it's not easy to complete this game, especially again with reinforcement learning, deep RL. But let's see. I've seen it happen, many times. So let's take a look at it and see how it goes. In the meantime, definitely, if there are other questions, I'm more than happy to answer.
Yeah. So does anyone have any question? It could also be related to any of the other slides or reinforcement learning in general.
Yes.
So Alessandro also shared lots of resources that you can use to start learning reinforcement learning if you're new to it, or maybe meanwhile you could also tell how many of you guys are already familiar with reinforcement learning or have worked with it. So actually we did have a few sessions on reinforcement learning where we talked about simple problems like cart pole balancing and so on. So I think at least a few people would be familiar with reinforcement learning here. So
I also have a question. Can you hear me?
Yeah.
Yes.
Yeah, Eric.
Okay, perfect. What we're seeing here is a reinforcement learning algorithm acting in a virtual environment, but you were talking before that about drones, which are acting in the real environment, and but they are trained in a simulation or something, right? In a virtual environment first, and then deployed in the real world.
Exactly.
So I wanted to know how you solve the difficulty of the difference between the environment that is trained in the virtual reality or virtually and then deployed in the real environment. There are differences. How can the agent deal with that?
Of course. Thank you for your question, Eric. It's a very important point, that one. So the transfer learning from simulation to the real world is one of the major problems, and reinforcement learning needs to deal with it, because as we were saying before, we need to train in virtual. Actually, let me clarify maybe one thing. What we are doing in the aerospace, my experience in the aerospace world is so far is only in virtual world. Okay, so we train and test in simulation. We at the moment we never translated it into the real world, but still, the problem is always more or less the same. So the idea there is, and the best solution found so far is leveraging what's they usually call simulation randomization. So the idea is the following: your simulator will hardly be perfect, and we hardly be representative. And in the meantime, we completed the game.
Yeah.
Yes. And against the resurrection too. So it's good, it's great. It's sometimes it's not the first time you see it's incredible, and actually it's something that I still enjoy a lot. And every new game is always a very good experience. So yeah, getting back to that. The point is, maybe your simulator will not be perfect, will not be 100% representative of the real world, but if you identify the parameters that are related with this uncertainty, for example, frictions in your actuators, or noise in your sensors, like your inertial measurements, or in your GPS. So if you're able to identify those uncertainties, and if you are able to model them and to let your controller face then a sampling of this uncertainty distribution, well, you will build something that is way more robust, and that will easily, I wouldn't say easily, but transfer to the real world in a better way, in a more frictionless way, let's say. I'm not sure if I was able to convey the idea. So simulation randomization is one of the best approaches in this regard.
Yeah, thank you. I think I understand. Maybe another question concerning that. If you're training in a simulation, is it possible to, for example, speed up the simulation to learn faster, or does that break the learning?
This is great. This is another great point. During we can also stop this one. Okay, we can just leave it go anyway. That's not a problem. Let me bring on again my slides. Here, here, when first of all, this of course is from OpenAI. Okay, just to make sure. And first of all, you see that there are multiple instances of your simulation in parallel. And so this is the first way in which you can speed up your training. So creating multiple instances, and this is of course available since you are playing in the virtual world. So you don't need to build like, I don't know, 100 drones. You don't have to build them, because in virtual worlds you can just need to create multiple parallel instances. So, and this is one way to speed things up. At the same time, and this could be good to show, let me just stop this. We can, and this is something that our environment allows, you can speed up execution. So, okay, sorry. Second minus. Okay, so we can. We were watching the real-time execution of the environment. So environment that are executed at nominal speed. While here you see we are taking a look at the environment executed at higher speed. So definitely this is a possibility, you see, and this is just a small option in our environment. So you can also deactivate rendering. I mean, letting it run in a headless mode without showing the graphics, and it speeds it up also even more. Without locking the FPS is another way. And now this is useful, usually something that you can do. Now there can be constraints that would limit your options in this regard. It depends on how fast is the simulator, but also the nature of your problem. Sometimes it is important to adhere to, for example, if I train a bot that is able to submit, instant, to play and send actions at 60 FPS, if my goal is to let that bot play against humans, maybe I need to put a limit in the speed, reaction times of my reinforcement learning agent, because otherwise I would be cheating or something like that. So speed is you can speed up training. You have to be careful depending on the problem you are solving. But in general, yes, training in virtual is how you speed it up, definitely.
Yeah. So we can take the last set of questions. Does anyone still have any question?
Hello. So actually, what you're saying is that I can train the robot to and teach it like in virtual, and which is actually gonna save me time and money. And when I run the hardest mode, it's gonna run faster because there are no graphics and stuff.
Well, I'll try to make it more clear maybe. So I'm saying that in the depending on the simulator you will be using, you need to you could speed it up training. Now I was making the example with our own environments. So the Umbra Arena, those environments about fighting games. Well, in our case, we can speed execution up in order to make training faster. So you have control in that, and the limit will be your CPU speed. In general, so this is only for our own specific environments. Actually, there are also other environments that allow these kind of things. Now, apart from our own environments, in general, yes, you could speed it up. in order to get something trained faster. Now about saving money and time, it depends, because if you already have, or you can easily build a simulation of your problem, a simulator of your problem, yeah, it could be the case that you will be saving time. If you need to build a good simulator from scratch, well, it is not 100% sure you're gonna save time in this way. It really depends on the problem and on the context. But in general, yeah, if you want to leverage RL, virtual environments are needed. And so, yeah, this is more or less the general answer.
Okay.
All right. Thank you. I got another question.
Yeah, please go ahead.
Yeah, so like, what if I try to run the simulation on a virtual computer? You know, like there are some apps that allows you to use virtual computers with really strong CPU and stuff. Yes. So what if I run on a virtual computer and actually use multiple profile, like multiple virtual computers, and then gather all the data received in one file? So how about that?
Yeah, sure. This is distributing experience collection. What is called experience collection is definitely a way to make things faster. Definitely, it is typically feasible, possible. You need to make sure you create the right pipeline in receiving and gathering. Let me go very quick to the slide about OpenAI. This was the infrastructure OpenAI was building. Now, as you can see here, they have like multiple. So first of all, 500 CPUs and one GPU, and this entire set is replicated for 256 times. So you need to, but you need to make sure, for example, to collect in the very same place all model parameters. These are network weights, and then distribute them to every single instance. And yeah, if you are able to do so, and they have an entire infrastructure doing that, well, it speeds things up, of course. Yes, so it is feasible.
Aren't they going to this virtual computer isn't going to do the same thing the others are doing? Because like if you start them in the same time and start running the simulation, I don't know, maybe they're going to do the same thing, so they're gonna actually gather the same data.
Okay, now, okay, I got your question. No, in this case, no, it depends on how you train things. So if you train against, for example, in these games here, like Street Fighter or others, every time you start a new game, you will not be facing the same opponent, for example. So there are random items in that. There are different difficulty levels and so on and so forth. And this is for the mode that we call AI versus com, where we mean our AI is fighting against the computer itself. Now, in this case, the case of OpenAI, and I tested it also on environments, there is also the self-play mode. The self-play mode lets you play, against yourself. And since at the very early stages, you will be using random agents, they will all be different. And the point is, the more different they are in the early stages, the more exploration you get, and the more probable will be finding a good policy. In fact, what you are suggesting, so that being let's say limited by having the very same data in all the parallel instances, can become a problem for self-play if you find if you fall in a suboptimal point of the policies, and you would be seeing the same agent going on and on with the same actions. So it's definitely something that is not easy to do a self-play in this way. But it is not the case. Just to give you an idea, in my implementation is represented here. no, here. I run 16 environments in parallel. So in order to collect gameplays, I run 16 instances of the game in parallel, meaning that I would be, if you see my training script, I'm instantiating 16 different environments that are going on in parallel. I collect those experiences that are all different, and I'm sending them to the same GPU to optimize the network weights.
Thank you.
Thank you for your question.
Perfect. Yeah. So, yeah, I think if anyone has any question, we can just take one more. We are over time, but that's fine. If anyone still has any question, we can take. Okay. No, then then I can conclude today's session. So thanks a lot, first of all, Alessandro, for this really amazing presentation, and for sharing this interesting GitHub repository that you're working on. And I would highly recommend everyone to actually just immediately start trying to work on it, because then it would be more fun, and you can actually learn it while you're programming and while you're actually doing. And also the interface, the programming structure is also very similar to what we use in OpenAI Gym and stable baselines. I think you're using those algorithms from stable baselines as well. So it's very user friendly and easy to use. And also, Alessandro, you have your own Discord server as well, right? So I'll share all of these details also in the announcements later on, and you can also go to Alessandro's server, and if you have any specific questions, I think you can connect with him and also ask him later as well.
Exactly. Thank you, Chanandip. Yes, exactly.
Perfect. Yeah. Then thank you very much again, and I'll get back to Alessandro to get the relevant resources, and I'll share it with you guys after this. So thank you everyone for joining this really amazing presentation. Yeah.
Thank you
all.
Thank you. Bye.
Thank you. I will try this.